We would like to welcome Fuming Chemicals Incorporated investors. We thank you for selecting us to present our compound for round one venture capital funding. Our company, Medius Chemicals, prides itself on providing the most competitive compounds. Medius Chemicals is made complete by a team which consists of CEO Lily Harrison, CTO Vu Huyen, and COO Anna Lawson. Today, we would like to propose to you a bid for our compound 5-hydroxy isophthalic acid. 5-hydroxy isophthalic acid can be used as the starting material for a wide variety of products, such as drugs, agrochemicals, and polymers. During our bid today, we will discuss with you how our product is made as well as the cost analysis.
Video, we will talk about the steps and mechanisms for the preparation of 5-hydroxy isophthalic acid from benzene. 5-hydroxy isophthalic acid. Here are the steps. Benzene is converted into toluene using chloromethane, aluminum trichloride. Toluene is then converted into benzoic acid using potassium permanganate, water, heat, sulfuric acid. Once we have benzoic acid, we will make toluic acid using aluminum trichloride, chloromethane. From M-toluic acid, we will make isophthalic acid using potassium permanganate, water, heat, and sulfuric acid. From isophthalic acid, we will use chlorine, aluminum trichloride to make 5-chloro isophthalic acid. And from here we will get to our final product, 5-hydroxy isophthalic acid using sodium hydroxide, sulfuric acid, and high temperature. Mechanisms. Step 1. Friedel-Crafts alkylation. Benzene is treated with chloromethane in the presence of aluminum trichloride. Aluminum trichloride is a Lewis acid. It functions as a catalyst, reacting with chloromethane to produce a carbocation. This carbocation is an excellent electrophile. It is capable of reacting with benzene, a very stable compound. This reaction is an electrophilic aromatic substitution reaction. In the first step, the aromatic ring functions as a nucleophile and attacks the carbocation, forming a sigma complex. This sigma complex has 3 resonance structures. The first step here is called the nucleophilic attack step. Then in the second step, the proton transfer step. The sigma complex is deprotonated, restoring aromaticity. This proton is being taken away. This bond is going in here, forming a double bond. The ring now has 3 double bonds. 3 double bonds like before. So it is again aromatic. Step 2. Oxidation at the benzylic position. Oxidation at the benzylic position can be accomplished with chromic acid or potassium permanganate. Here we use potassium permanganate. Any alkyl group on an aromatic ring will be completely oxidized to give benzoic acid, provided that the benzylic position has at least one hydrogen atom. Here at this benzylic position, we have 3 hydrogen atoms. The mechanism for this reaction is complicated and not fully understood. The scientific community hasn't figured it out yet. The textbook doesn't discuss it. Step 3. In step 3, we repeat step 1 and step 2 to add a second carboxyl group on the benzene ring. In step 1, we added an alkyl group on the ring, and in step 2, we oxidized that alkyl group, turning it into a carboxyl group. So in step 3, we repeat those 2 previous steps to add a second carboxyl group to the ring. Notice here that this second carboxyl group is added to this position. That is because the first group, the carboxyl group is a meta-directing deactivator. So it directs the incoming group to this meta position. Step 4, chlorination. Chlorination of benzene is accomplished with a suitable Lewis acid, in this case, aluminum trichloride. This mechanism involves 2 steps. The first step is the nucleophilic attack step. In this step, the aromatic ring functions as a nucleophile and attacks the electrophilic reagent, resulting in a sigma complex. This sigma complex has 3 resonance structures. Then, in the second step, the proton transfer step, the sigma complex is deprotonated, restoring aromaticity. This proton is being taken away, and this bond now goes in here, forming a double bond. The ring now is again aromatic because it has 3 double bonds as it did before. Now we have made 5-chloroisophthalic acid. We've come to the final step, step 5, elimination, addition. This reaction occurs under significantly high temperature and pressure. The temperature is 350 degrees Celsius. The reagents used are sodium hydroxide and sulfuric acid. Sodium hydroxide is a base. A base and an acid are put together, they will neutralize each other. That's why sodium hydroxide must be added separately from sulfuric acid in step 1, and then in step 2 we add sulfuric acid. The mechanism, the elimination addition mechanism, proceeds first by the elimination of hydrogen halide. The product of the elimination is highly reactive. It contains a benzene ring. It reacts rapidly with any available nucleophile to give an addition product. The first step Proton transfer. Hydroxide functions as a base and deprotonates the aromatic ring. Hydroxide is taking this proton away, and this bond is going in here, making a lone pair on this carbon. This lone pair will then form a bond. But now this carbon has too many bonds. 1, 2, 3, 4, and then the newly formed bond 5. Carbon cannot have more than 4 bonds. So this bond has to be broken and this group has to go away. Chloride is a good leaving group. It is leaving, taking the electrons with it. It now has an octet, so it's leaving happily. The product of the elimination is this benzene derivative. It has a triple bond here on a ring. Proton transfer here, loss of a leaving group here, and now we have a nucleophilic attack reaction. Hydroxide functions as a nucleophile and attacks benzene, this benzene ring. This reaction adds a group, the hydroxy group, on the ring, and it also put a lone pair on the next door carbon. In the final step of this mechanism, this elimination addition mechanism, the resulting anion removes a proton from water to yield the product, the final product of this entire process, 5-hydroxy isophthalic acid. So this final step is a proton transfer. Elimination addition. In elimination addition, we have performed proton transfer, loss of a leaving group, nucleophilic attack, and proton transfer. We begin with a proton transfer and we end with a proton transfer.
Hello, welcome to the cost analysis portion of our presentation. In this part, we're going to be talking about how much Medius chemicals will be able to make if they decide to invest in 5-hydroxy isophthalic acid. And to do this, first we need to look at how much it will cost to synthesize the compound. And to find that cost, what we first need to do is look at how much the reagents are going to cost to synthesize. So we have aluminum chloride at 10 cents per gram. We have chloromethane at $1.63 per gram. We have potassium permanate at 37 cents per gram. Chlorine is 77 cents per gram. And sodium hydroxide is 3 cents per milliliter. And distilled water is going to be 29 cents per milliliter. This will give us a total cost of $3.19 to synthesize this compound. And now, after we get that information, we need to figure out how much our competitors are selling that compound for. And here we can see that on average, our competitors are selling the compound for $5.78. Now, if we take that number and minus what our cost was for the reagents, we'll be getting $2.59. Now this is significant because it will give us a huge percent gain of 81.19%. This will allow us to get a huge return on our investment for synthesizing this compound.
Investors of Fuming Chemicals Incorporated, your motto is where dreams are realized or crushed. Well, don't let this dream deal pass you by. Who can say no to an almost 82% gain? We have our competitors beat. Invest in Medius Chemicals and let's make this dream a reality.